Welcome back to the Deep Dive. Today we are taking a trip directly inside the wires. We're talking about the very infrastructure that makes, all modern electronic communication possible.
Right.
Our sources today are foundational technical materials. We're talking core engineering concepts that define how we move high-frequency energy reliably, whether that's for, say, shipboard radar or a massive terrestrial data network.
And this is a deep dive that's really tailored for technical clarity and for maximum retention.
Okay.
Think of this as the essential study guide for an exam, or maybe the foundational technical background you'd need to write a compelling policy memo on system efficiency.
Right.
We are breaking down some pretty complex physics into clear definitions, elegant formulas, and I think most importantly, the critical cause and effect relationships that govern every single RF system out there.
Okay, so let's unpack this mission immediately then. We are talking about transmission lines.
Exactly.
And they are really the unsung heroes of electronics. Their mission statement, it sounds simple, but it's just immensely critical. A transmission line is a specialized device designed to efficiently guide electrical energy, specifically high-frequency RF energy, from one point to another.
And that word guide is so important. When we say guide, we mean doing so with the express purpose of transferring that energy with the least possible power loss.
Ah, okay. So loss is the enemy.
It's the ultimate enemy. I mean, think about it. If you're building $1 million transmitter, you absolutely cannot afford to lose half that energy just heating up the cable between the transmitter and the antenna.
Right.
Every single decibel of loss is lost range, lost data, and frankly, a wasted operational budget.
So we're viewing this from the perspective of the source material. This is foundational electronics training, which means we have to master the language, the jargon.
You have to speak the language. And the first step is really just naming the anatomy of the system.
Okay.
When we talk about a simple two-wire line, we define its two distinct ends based on their function. The end connected to the power source, the part that's generating the energy. We call that the input end.
The input end.
Right.
And you'll see that end referred to by several critical aliases, right?
That's right.
It's the transmitter end, the generator end, or sometimes just the sending end. If you're looking at a technical schematic, those names are basically interchangeable.
They are, but they all refer to the same point, the point where the wave originates.
Okay, so that's one side. What about the other?
Conversely, the other end, the part that, consumes or radiates the energy, so the antenna, the receiver, maybe a termination resistor, that is the output end.
And I'm guessing the output end has just as many names.
It does. You'll see it called the antenna end, the receiving end, the load end, or sometimes the sink.
So in essence, the transmission line is just the bridge between the source, the input or generator, and the load, the output or antenna.
Exactly. And understanding that relationship is absolutely key because so much of the theory we're about to get into is about what happens when the source and the load don't agree, when there's a mismatch.
So let's pause here. A quick structure check, especially for your exam prep. The fundamental definition. A transmission line guides RF energy from the source to the load with minimal loss.
That's it. The entire goal of all the engineering choices we're about to discuss today will be to achieve that minimal loss.
Excellent. So now that we know what the line does, let's get into how it's built. We need to move from this abstract concept to the physical reality of the wires and tubes that carry this energy.
Exactly. We are moving into the physical structure of these transmission mediums. And it is so important to note that every medium, from the simplest parallel wire to the most complex waveguide, has specific engineered properties.
Like what?
Well, a characteristic impedance, a specific current carrying capacity, and a design that's tailored for a specific frequency range, a power level, and an installation environment. The physical structure literally determines its capabilities and its limitations.
Okay, so let's break down the 5 primary categories that govern almost all guided RF transmission. We can start with the historical basics.
The first one is structurally the simplest, and to be honest, it's often the least efficient for modern uses. The parallel line, or two-wire open line.
Structurally, it's exactly what it sounds like, right? Just 2 parallel conductors, and they're held at a uniform distance.
Typically 2 to 6 inches apart, and they're held there by these solid insulating spacers.
I think I can picture this, like old high-tension power lines, or maybe those legacy rural telephone wires you still see sometimes.
You've got it. And it's effective for lower frequencies and high power, but it has some major weaknesses.
Okay, so here is the critical cause and effect relationship you need to remember for this design for your exam.
Yes. Due to the wide spacing and the complete lack of any shielding, These lines suffer from very high radiation losses.
Unpack that for us. What does radiation loss mean in practical terms?
Okay, so think of it this way. The alternating current is generating magnetic fields around the conductors. Because
Huh?
these conductors are relatively far apart, the fields don't perfectly cancel each other out. So they leak into space. They radiate energy away from the line, almost like a highly inefficient antenna.
So you're not just losing power, you're also broadcasting it where you don't want to,
Exactly. And not only does this waste power, but it also allows the line to easily pick up external interference. This leads to high electrical noise pickup.
which makes the parallel open line functionally useless in a high-density electronic environment,
Right.
like a city or a modern ship.
Absolutely useless. It's a relic for most high-frequency applications.
So if you need something a bit more manageable, but you're still using parallel wires, you'd move to the two-wire ribbon, which most of us would recognize as twin lead.
Ah, yes. If you're of a certain age, you definitely remember being told to go wiggle the TV antenna that was connected by that flat plastic ribbon cable.
I do.
Structurally, it's just two parallel wires precisely embedded in a thin layer of low-loss dielectric, usually polyethylene. The key technical improvement here over the open line is that you have guaranteed uniform spacing.
Which helps stabilize its electrical behavior, I assume?
It does, but it still lacks any significant shielding, so it's still susceptible to noise.
Okay, next up is the twisted pair. We see these everywhere in infrastructure, right?
Yeah.
Especially in older data and telephone systems.
Yes, this is literally two insulated wires twisted around each other to form a flexible line. The twisting is actually a clever, low-tech way to minimize low-frequency noise pickup.
How did that work?
By twisting them, you ensure that any external electromagnetic interference hits both conductors almost simultaneously, but with opposite phases relative to the signal. So the induced noise on each wire mostly cancels itself out.
Clever. But there's a major technical drawback, and it's tied specifically to the material needed for flexibility.
This is a critical cause and effect point. The need for a flexible insulating jacket, which historically used rubber effect. These lines are strictly not used for high-frequency RF applications.
Why not?
Because of the high dielectric losses inherent in that rubber insulation. The material itself just absorbs way too much energy when it's subjected to these fast-changing fields. The total power loss becomes unacceptable.
Okay, so that brings us to the first true high-performance structure, the shielded pair. This is where we start getting serious about confining the energy.
We are. The structure is a bit more complex. You have two parallel conductors separated by a solid dielectric, and then the whole thing is encased in a braided copper tubing.
That's the shield.
That is the shield, and it's generally connected to ground. The primary advantage here is isolation, which is just crucial for modern systems.
How so?
Well, for one, the conductors are balanced to ground, which means they're less susceptible to ground loops and external voltage differences. But most importantly, that outer shield isolates the internal conductors from stray magnetic fields. It practically eliminates noise pickup and reduces those radiation losses to negligible levels.
So if your policy memo is about signal integrity in a noisy environment, this is your minimum required technology.
Absolutely. This is the baseline for professional-grade audio and data.
Okay, so the fifth category is the one that's really dominant for general RF transport, the coaxial line. And we divide this into two subtypes.
We do. First, you have the rigid air coaxial line. This is high-end, high-power stuff.
Describe the structure.
It features an inner conductor that's mounted concentrically inside a tubular outer conductor. And they're separated only by minimal insulating spacers, often made of very low-loss materials like Pyrex or polystyrene.
The engineering elegance here is just astounding. The electric and magnetic fields are almost perfectly confined between those two conductors.
They are. This ability to minimize radiation losses is its chief advantage. It's a perfectly shielded, highly efficient channel for energy.
But I hear a but coming.
There's a big but. There are massive operational challenges that restrict its use. First, it's expensive to build, requires very precise construction, and crucially, it must be kept absolutely dry.
Why? What happens if moisture gets in?
It can cause leakage and, at high power, flashover between the conductors, an arc. To manage this, an inert gas like nitrogen, helium, or argon is pumped into the line at high pressure, sometimes up to 35 psi.
Wow, that's a huge operational cost just to keep the air dry. It sounds more like a complex plumbing system than a cable.
It really is. And you can't just seal it perfectly because of thermal expansion and contraction over long runs. It's impossible without sacrificing structural integrity.
So the gas pressure is a preventative measure.
Exactly. The pressure ensures any tiny leak is an outward leak of inert gas, which prevents moisture or corrosive air from seeping in. But even with all this care, high-frequency losses still limit the practical length of these lines.
Okay, so what's the second more common type?
That's the flexible solid coaxial line. This is the familiar coax cable you see connecting your modem or your satellite dish.
Right.
This uses a continuous solid insulating material like polyethylene, separating the inner conductor from the braided outer conductor. And polyethylene was a huge advance in the 1940s and 50s.
Why was that?
Before that, rubber insulation was common, but rubber, as we said, caused excessive high-frequency losses. It made high-power radar installations nearly impossible. Polyethylene changed the game.
The advantages here are obvious.
Yeah.
Flexibility, lower cost, and it's much more resistant to environmental contaminants like moisture, oil, or gasoline. That's essential for mobile or field applications.
It is, but we have to note that the continuous polyethylene, while it is a low-loss material, still introduces slightly higher loss than the pure air dielectric used in the rigid type. It's always an engineering trade-off.
Always a trade-off. Okay, and finally, a quick note on the structure that takes over at extremely high frequencies.
Waveguides.
And these aren't wires at all, are they?
Not at all. They are hollow metal tubes, either rectangular or cylindrical, that transfer energy by containing the electromagnetic wave within their walls. They look like ducts or pipes.
And what's the key behavioral quirk here? How does the energy move?
Well, the electromagnetic energy actually travels through a waveguide at a group velocity that is slower than its speed in free space.
Slower.
Why? It's due to the constant reflection of the wavefront off the inner walls of the tube. It's essentially bouncing its way down the pipe. This confinement and manipulation of the wave is fundamental to how they work.
And the installation challenges must be severe.
Oh, they are. Because the tube itself is the transmission medium, any physical damage acts as an impedance discontinuity. Dents, obstructions, poor flange connections, they all greatly increase attenuation or loss.
And they can raise the risk of voltage breakdown.
For sure. And here's a crucial dimension restriction for your notes. If the radius of any bend in the waveguide is less than 2 wavelengths, the attenuation becomes excessive. You just can't coil up a waveguide like a cable.
Okay, so let's quickly consolidate this structure versus loss concept. You have parallel open lines.
High radiation and noise loss.
Twin lead.
Better spacing, but still pretty noisy.
Twisted pair.
Terrible for RF due to dielectric loss in the insulation.
And then the high performance options. Shielded pair.
Good isolation.
And finally, coax and waveguides.
The best for field confinement. The choice is always a deliberate balance between the acceptable loss, the frequency you're using, and of course, the cost.
That's a great segue because now we need to talk about why the energy moves the way it does inside these structures. We're shifting from the physical build to the underlying electrical theory, the electrical model.
And we must immediately correct the most common misconception right out of the gate.
Go for it.
In almost all introductory electronics courses, you deal with circuits using what we call lumped constants.
Meaning a resistor, a capacitor, a coil. The properties are concentrated into single definable physical devices.
Exactly. You can hold it in your hand. But a transmission line fundamentally defies that model. It is described by distributed constants.
Okay, explain the practical difference between those two concepts for me.
Imagine a conventional circuit. You have a bucket, which is your capacitor, and a pipe with a constriction in it, which is your resistor. The properties are isolated in specific places.
Yeah.
In a transmission line, those properties are spread uniformly and continuously along the entire length of the line. The line itself is the circuit. Every millimeter of it has some resistance, some capacitance, some inductance.
So it's not like there's a capacitor in the line is the capacitor.
You've got it. It acts like a leaky, stretchy garden hose that also stores rotational energy along its entire length. It's a much more complex model.
And there are 4 core constants distributed along every millimeter of the line. We need these definitions locked down for your exam.
Let's do it. First, inductance. This is caused by the magnetic field that's set up by the current flow.
Okay.
Since the current is constantly alternating, the resulting magnetic fields are constantly expanding and collapsing. This induces a counter voltage that opposes the change in current. We express it quantitatively in microhenries per unit length.
Okay, that's L number 2.
Second, capacitance. Because a transmission line consists of 2 parallel conductors separated by a dielectric material, even if that material is just air, It inherently acts as a capacitor.
So it stores energy.
It stores energy in the electric field between the conductors, and we express this in picofarads per unit length.
Okay. Third constant.
Third is resistance, R. This is the simple one. It's the straightforward DC resistance of the conductor material itself, the physical impediment to current flow. And its energy is dissipated as heat. We measure it in ohms per unit length.
And the fourth, the one that's often forgotten, conductance G.
Yes. Conductance G is the reciprocal of resistance, but it's specifically referring to the shunt path between the two conductors.
Is a leak.
It's a leak. It represents the small amount of current, which we call leakage current, that flows directly through the imperfect dielectric, bypassing the load entirely. No insulator is perfect, so there's always a tiny parallel current path wasting energy. And it's typically expressed in microohms per unit length.
So these four constants, L, C, R, and G, are just unavoidable properties of any real-world conductor system.
They are, and they lead directly to system inefficiency via losses. We really need to focus on the three main types of loss because this is where all the engineering ingenuity is applied.
Right. Loss is the enemy of efficiency. Any loss reduces conductivity and limits the total energy available to the load.
And in sensitive systems, it can cause critical failures.
Okay, type 1. Copper losses or by $2 loss.
This is the standard resistive loss. It's straightforwardly dissipated as heat in the conductors. And remember, if you double the current, the power loss to heat quadruples. It's a squared relationship.
But this simple loss gets dramatically more complicated at high frequencies.
It does, and it's because of the skin effect. This is absolutely essential knowledge for anyone dealing with RF.
Let's nail the mechanism of the skin effect for everyone. Cause. As the frequency of the AC current increases, and we're talking especially above 100 megahertz, the rapidly changing current generates magnetic flux that opposes the electron flow.
Right, and that opposing magnetic flux density is strongest at the very center of the conductor.
Okay, so what's the effect?
The effect is that this pushes the electron movement away from the center. It effectively confines the current flow to the conductor's outer surface, or its skin.
So it's not using the whole wire anymore.
It's not. This significantly reduces the effective cross-sectional area that's available to carry the current. And since resistance is inversely proportional to cross-sectional area, resistance, and thus your $2 power loss, increases dramatically as frequency goes up.
Yeah, it's fascinating. So if you're running signals at 30 gigahertz, the copper at the core of your wire is literally doing almost nothing.
It's just along for the ride, which is why the engineering solutions are so clever. You can plate the conductors with a highly conductive material like silver because the current only uses the surface anyway.
Or for really heavy-duty systems.
You use hollow tubing. You just eliminate the useless copper mass in the middle while maintaining the necessary surface area on the outside.
Brilliant. Okay, type 2, dielectric losses.
This loss results from basically molecular friction within the insulating material itself. The alternating electric field is constantly stressing the dielectric. The electrons in the atoms are being forced to shift their orbits and distort.
And that constant shifting requires energy, which is then dissipated as heat within the dielectric material.
Exactly. And that's why material choice is so critical. Low-loss dielectrics like polyethylene are chosen specifically because their atomic structure is difficult to distort, which minimizes this internal heating.
Compared to high-loss materials like rubber.
Right, which can get surprisingly hot in high-frequency operation.
Okay, in type 3, radiation and induction losses.
These are the losses related to external field leakage. This is the whole reason we invented shielding in the first place.
So radiation loss is energy that just, it just projects away from the line into space?
Pretty much. The magnetic lines of force surrounding the conductor fail to collapse back into the system when the current reverses direction. That wasted energy is no longer available to your load. It's a huge problem for unshielded lines.
And induction loss is related, but it involves nearby objects.
That's right. The electromagnetic field induces currents in adjacent metallic structures. A nearby piece of equipment, a bulkhead, a grounded pipe. That induced current then dissipates power as heat in that external object, which represents power that was stolen from your primary transmission system.
Okay, so let's review the electrical fundamentals for our exam prep. Every line is governed by distributed constants, L, C, R, and G. The three major power sinks, or losses, are $2 loss, which gets much worse with frequency due to the skin effect.
Dielectric loss, which is governed by your choice of insulator material.
And radiation induction laws, which is governed by how effective your shielding is, like the copper braid and
You've
quico.
got it.
Right.
And mastering these constants leads us directly to the core mathematical relationships that predict how a wave will behave on the line. Which brings us to section 4, core theory, the constants of speed and resistance.
Let's start with a concept that I think often trips people up. Electrical length.
Right. Short and long are not physical measurements in the world of RF. They are completely relative terms.
How are they defined then?
The electrical length of a line is defined by comparing its physical length to the wavelength, lambda, of the energy it's carrying. And remember, wavelength is inversely proportional to frequency. The higher the frequency, the shorter the wavelength.
Let's use the numbers to make this concrete, because this is crucial for your memo. Imagine a line that is physically 3 meters long.
Okay.
If we send a low-frequency signal through it, say 30 kilohertz, the wavelength is enormous. It's about 10,000 meters or 6 miles.
Right.
So compared to a 6-mile wave, your 3-meter line is electrically very short. Its internal properties, like its inductance and capacitance, they barely affect the signal.
Now, keep that exact same 3-meter line, but run a high-frequency microwave signal through it, say 30,000 megahertz.
Okay.
The wavelength at that frequency drops to about 0.01 meters, so roughly 1 centimeter. Now, compared to a centimeter-long wave, your 3-meter line is electrically very long.
And the implication here is critical. If a line is electrically long, you absolutely must account for its distributed constants and its impedance.
You must, because the voltage and current patterns along that line will oscillate and fluctuate wildly. If it's electrically short, you can often just treat it as a simple piece of wire. Frequency defines reality in this domain.
This frequency-dependent reality brings us to the velocity of propagation, v.
Which is the speed at which the wavefront travels down the line. And this is not the speed of the electrons themselves, it's the speed of the energy, the voltage change.
And it's constant rate for any given line.
It is. And it's determined only by its distributed inductance, L, and capacitance, C.
The mathematical derivation is pretty elegant. By relating the fundamental electrical properties involved in charging the line's capacitance and inducing a magnetic field along its inductance, we find that the time t it takes for the energy to travel a unit length is governed by the square root of the product of L and C.
Specifically, the formula is 2dd is Mars square TLC. And since velocity is defined as distance, d, divided by time, t, we arrive at the foundational formula for wave velocity in a transmission line.
That's Vd over the square root of L times C. Let's illustrate the calculation. Imagine a 1,000-foot section of line for our distance, d.
Okay.
And let's say L is 0.25 microhenries, and C is 1,000 picofarads per that unit length. When you plug those values into the formula, the travel time, t, calculates out to 0.5 microseconds.
So if the wave takes half a microsecond to travel 1,000 feet, you just do the division. The velocity is a staggering 200 million feet per second.
And that velocity is locked in the moment the line is manufactured.
It is. It's based entirely on the materials and the spacing that define its L and its C.
And this brings us to what might be the pinnacle of transmission line theory, characteristic impedance, or Z0, $.
Yes. If you are preparing for any high-frequency exam or writing a policy advocating for system standardization, this is the single most important concept to master.
So what is it?
$. Is the ratio of voltage to current I at every single point along the line if, and this is a big if the line is either infinitely long, so the wave never returns, or if it is terminated in a perfect resistance that is exactly equal to $2.
And this impedance value is inherently independent of the line's length.
That's right. And its significance is all about maximum efficiency. $. Defines the key to maximizing the transfer of electrical power.
Okay.
When the load impedance is perfectly matched to the line's characteristic impedance, $, the energy travels down the line, is entirely consumed by the load, and there is zero reflection. None.
The policy implication there is crystal clear. Matching $to $, a line is the mandate for efficient operation. If you fail this match, you are losing power and you are losing reliability.
And just like velocity, $, is also defined solely by those same distributed constants, L and C.
And the core formula that governs that perfect ratio of E to I is
Z0 equals the square root of L divided by C.
the elegance there is really something. Velocity is the square root of the product, L times C. Impedance is the square root of the ratio, L divided by C.
Exactly. The physical dimensions and material choices that set L and C define both the speed of the energy and the required resistance for maximum power absorption.
So let's use our previous example. L was 0.25 microhenries and C was 1,000 picofarads.
Right.
Plugging that into the Z-dollar formula, the math gives us a characteristic impedance of 500 ohms.
And that is the magic number for that specific line. And if you look at actual practice, the characteristic impedance of lines used in telecommunications, radar, and broadcasting, it normally lies within a pretty practical range, typically between 50 and 600 ohms.
This is why you see standards like 50 ohms for RF communications and 75 ohms for video systems.
Exactly. Those are the standard Z-dollar values that are defined by the manufacturing specs of the cables.
Okay, let's quickly recap the math and the mission. Electrical length is relative to frequency.
Wave velocity, V, is set by L and C.
Characteristic impedance, Z-dollar is also set by L and C.
And achieving the match, Z-dollar is the fundamental technical requirement for maximum power transfer and minimal system reflection.
Okay, so now let's step back and look at the energy flow itself. We're moving into section V wave propagation, analyzing the actual movement of energy down the line. Let's start with a simple thought experiment.
Okay, imagine applying a simple DC voltage from a battery to a long transmission line. When you close that switch, what happens?
That initial electrical pressure, the voltage difference, moves down the line as an electrical wavefront. The moving electric field and the accompanying magnetic field, together, they constitute a simple electromagnetic wave that's traveling toward the load.
And since the voltage is constant, because it's DC, and assuming the line is lossless, then the energy reaching the load is exactly equal to the energy that was developed at the battery. Once the line is fully charged, it all settles down, and the line just looks like a simple resistive load after that initial transient wave has passed.
Okay, but here's where it gets really interesting.
Yeah.
When we apply AC, specifically high-frequency RF,
Right.
the AC generator produces a continuous cyclical sinusoidal voltage wave. And this wave is constantly propagating down the line.
And now we must deal with two distinct wave components, and this is the source of all the complexity we're about to discuss.
Okay.
First, you have the incident waves. These are the voltage and current waves traveling from the generator to the load. This is the energy that's supposed to be doing the work.
And second, you have the major problem.
The major problem. If the load is not perfectly matched to Z-dollars, the load cannot absorb all of that incident energy, and that excess energy can't just vanish. It has to go somewhere.
So it's sent back.
It is immediately sent back. These are the reflected waves traveling from the load back toward the generator.
And this reflection phenomenon is the very definition of system inefficiency.
It is. It means power is just bouncing around inside your transmission channel instead of being delivered to the antenna or the receiving device where it belongs.
So quick check for our notes. Incident wave is source to load. Reflected wave is load to source. And it's caused by any mismatch between the load impedance, Z-dollars, and the line impedance, Z-dollars.
Perfect.
So we've now arrived at section 6, the mismatch problem. This is the heart of what engineers spend all their time fighting reflections and their consequences, standing waves.
And to really grasp the complexities of AC reflection, it's actually best if we first look at the simple DC edge cases. They define the polarity shifts that happen when a wave hits an extreme mismatch.
Okay, so case 1, the open-ended circuit. This is the worst mismatch possible. The load impedance, $, is infinite. When that DC wavefront hits this open gap, what happens?
The voltage reflection occurs with the same polarity and amplitude as the incident wave. So if the incident voltage was positive, the reflected voltage is also positive. The result is a momentary doubling of the voltage right at that open end.
Okay, so voltage doubles. What about the current?
Well, the current can't pass the open circuit, so the current reflection comes back with the opposite polarity, which cancels the incident current out, forcing the resultant current to 0 right at the open point.
Got it. Now, case 2, the short-circuited circuit, the opposite extreme. Load impedance, $, is 0. The situation flips entirely here.
It does. When the wavefront hits the short, the voltage reflection comes back with the opposite polarity. If the incident voltage was positive, the reflected voltage is negative. They cancel out, forcing the resultant voltage to 0 at the shorted end. Rhoda current reflection, however, returns with the same polarity, which causes the resultant current to double momentarily right at the shorted end.
So the takeaway from this DC analogy, which is crucial for understanding AC waves, is that an open circuit reflects voltage in phase, but a short circuit reflects voltage out of phase, and the currents do the opposite.
Precisely. Now apply this to a continuous AC signal. When the incident, the outgoing, and the reflected, the return waves meet on the line, they are continuously adding together algebraically, point by point.
And the resultant wave is no longer traveling. It just appears to be oscillating in a fixed position.
And that is the definition of a standing wave.
And crucially, standing waves are caused only by reflections, which in turn only occur when z-Lars is not equal to z-Lars.
That's the key. When the match is perfect, you have a traveling wave, or what we call a flat line. When the match is imperfect, you generate these stationary patterns.
And this is a point of real engineering stress. The standing wave pattern creates fixed points of maximum voltage, called voltage loops, and minimum voltage, or voltage nodes.
And the presence of those voltage loops can push the peak voltage beyond the insulation limits of the line, which risks catastrophic breakdown and flashover, especially at high power.
We also must remember the phase relationship between the two key standing waves.
Yes, the voltage standing wave and the current standing wave are always separated by 90 degrees, or a quarter wavelength.
Which means where the voltage is at its maximum, the current is always at its minimum, and vice versa.
Always. This leads us to the ultimate distinction in system design, resonant versus non-resonant lines.
And the ideal, the engineering goal, is the non-resonant line, also called a flat line, or an untuned line.
Right, and the definition, a line that has no standing waves of current or voltage.
And the condition for a non-resonant line is simple. It must be terminated in its characteristic impedance. Z-Lars law must equal Z-Lars laws.
When that condition is met, all the incident energy is absorbed, there are no reflections, and the line operates with maximum efficiency. This is the absolute gold standard for high-speed digital communications and high-power applications.
The alternative, then, is the resonant line, or a tuned line.
Which is, by definition, a line of finite length that is deliberately not terminated in its characteristic impedance. So Z-low does not equal Z-Dollars.
Reflections occur, creating those standing waves. But why would you ever want standing waves? It sounds like a bad thing.
Well, it's because the resulting impedance along the line changes in a very predictable way based on its electrical length. This allows engineers to use the line segment itself as a precise tuning device, like a simulated lumped circuit component.
So this is an advanced application that's essential for high-frequency circuits, where, physical inductors or capacitors are impractical because of their size or their losses.
Exactly. Let's look at how specific lengths of these resonant lines act. Take open-ended lines. The load is essentially infinite impedance.
Okay, so if the line length is an odd quarter wavelength, so 1/4 lambda, 3/4 lambda, and so on,
the voltage at the input will be minimum, the current will be maximum, and therefore the input impedance will be minimum. It acts electrically just like a series resonant circuit. It looks like a very low resistance, almost a short circuit.
and if that same open-ended line is an even quarter wavelength, so a half lambda, 1 full lambda,
Then the voltage is maximum, the current is minimum, and the input impedance is maximum. It acts electrically like a parallel resonant circuit, an extremely high resistance. It looks like an open circuit.
and for shorted lines, I'm guessing the effects are completely reversed.
They are, because of that initial polarity reflection shift we talked about with the DC case.
So shorted lines at odd quarter wavelengths act like a parallel resonant circuit,
High resistance.
and shorted lines at even quarter wavelengths act like a series resonant circuit.
Low resistance. This ability to transform impedance based purely on length is a profound consequence of the standing wave pattern, and it offers critical versatility in microwave design.
Okay, let's pause and synthesize. Mismatch, where z-Lars is not equal to z-Lars, causes reflections.
Reflections create standing waves.
Standing waves are bad for power transfer, but they can be used intentionally in resonant lines to mimic reactive components like inductors and capacitors, using just specific lengths of cable.
You got it.
And since the goal of any robust system is efficiency, we need a single metric that instantly tells us how badly we have failed the matching test.
That metric is the standing wave ratio, SWR, which brings us to Section 7, quantifying performance.
So SWR is the report card for your system's termination. It tells you exactly how close you are to that ideal non-resonant state of maximum power transfer.
That's right. And the primary metric we use is the voltage standing wave ratio, or VSWR. This is defined simply as the ratio of the maximum voltage, Emax, to the minimum voltage, Emin, measured along the line.
So the formula is just VSWR equals Emax divided by Emin.
That is the formula you must memorize. And the ideal condition, that perfect flat line where Emax actually equals Emin because there are no reflections causing deep dips, results in an SWR of 1:1.
That's the non-resonant line, the engineering ideal.
It is. Conversely, the higher the VSWR goes above 1:1, say 3:1 or 5:1, the greater the reflection coefficient and the greater the inefficiency and power losses due to all that circulating energy just heating up the line.
In a perfectly open or shorted circuit, E-min approaches 0, and the VSWR approaches infinity.
Which is a system operating under immense, potentially destructive stress.
I've also heard of the power standing wave ratio, or PSWR.
Yes, you'll see that in older documentation. It's mathematically defined as the square of the voltage standing wave ratio.
So PSWR is just Emax squared divided by E-min squared.
Right. But it is important to note the potential confusion here. Although the name implies it's a ratio of maximum to minimum power, power along the line itself doesn't actually vary proportionally to this ratio.
So it's a bit of a misnomer.
It is. PSWR is fundamentally just a measure that's proportional to the square of the voltage ratio, and it's mainly used by specific types of detection instruments that happen to be more sensitive to that squared relationship.
Okay. So the ultimate tool for understanding why a VSWR is bad and whether it's behaving more like an open or a short circuit is the reflected voltage formula.
Yes, this allows us to quantify the exact amount of reflected energy, E sub r, relative to the incident energy, E sub I. And the reflection coefficient formula is
ER equals EI times the quantity of RL minus Z naught, all divided by RL plus Z naught.
And that formula is incredibly powerful because it explains the polarity behavior we observed back in the DC cases.
Okay, walk me through it. Scenario 1. The load is too large. The load resistance, they're greater than Z dollars.
Then the numerator minus Z dollars is a positive number. Therefore, E dollars is positive, and the voltage reflects back with the same polarity. This is an underloaded, open circuit-like condition.
Got it. Scenario 2. The load is too small. If Y dollars is less than Z dollars,
Then the numerator is negative. Therefore, E dollars is negative, and the voltage reflects back with the opposite polarity. This is an overloaded short circuit-like condition.
and of course, if $3 exactly equals Z dollars, the numerator is 0, E dollars is 0, and you have achieved a perfect match and an ideal one-to-one VSWR.
Exactly. This formula is the definitive mathematical guide for diagnosis and troubleshooting line performance.
Okay, to finalize our metric mastery for the exam, VSWR, which is Emax over Emin, is the key metric of termination quality. One-to-one is the ideal non-resonant target.
And the reflection coefficient quantifies the scale of the mismatch and defines whether the load is electrically too large, which is open-like with a positive reflection, or too small, which is short-like with a negative reflection, all compared to the line's inherent Z dollars dual.
Right. We've covered the structures, the constants, the wave behavior, and the critical metrics. Now let's synthesize all this information. This is Section 8. Final takeaways. What does this technical mastery actually mean for system performance?
For your exam prep and for your policy memos, the overarching lesson here is that a transmission line must never be treated as a passive piece of wire.
Right.
It is a highly specialized, active component that is defined by those distributed constants, L, C, R, and G. Technical mastery of this domain is the difference between a highly efficient, reliable communication system and one that is unstable and prone to failure.
And the foundational goal is always engineering a system where the load is matched to the characteristic impedance ZL equals Z dollars.
That's right. And that results in the sought-after non-resonant line status, which maximizes power transfer and gives you that beautiful one-to-one VSWR ratio.
Any failure to match generates standing waves, which is the sum of the incident energy you sent out and the reflected energy that bounced back.
And these standing waves are not just academic concepts. They cause massive localized power dissipation, they generate dangerous voltage peaks that can destroy equipment, and they fundamentally degrade your signal quality.
And remember the enemy of high-frequency operation loss.
Always. The resistive I2 over copper loss increases exponentially with frequency because of the skin effect, which forces engineers to use plating and hollow conductors. And dielectric losses require constant vigilance in materials science, choosing low-loss insulators over older materials like rubber.
So this entire field, the selection of the right line structure, the calculation of Z dollars line, and the aggressive minimization of VSWR, this is what allows everything from high-resolution satellite imagery to complex military communications to function reliably across huge distances and bandwidths.
It is truly foundational technical mastery.
Okay, so we have spent this time focusing on traditional systems wire lines and hollow metal waveguides, where the physics of Z naught equals the square root of L over C perfectly governs the matching requirement.
Yes. But, as we mentioned, modern telecommunications rely so heavily on optical fibers, where RF waves are replaced by light waves traveling through glass.
So consider the magnitude of the engineering challenge here. We've just detailed the extreme complexity of preventing wave reflections in simple copper lines. Now, imagine a fiber optic cable carrying thousands of wavelengths of light per millimeter.
Light still bounces, Internal reflections still occur, and they impact the signal purity and the data rate just the same.
So the provocative thought for you to take away is this. Does the concept of characteristic impedance, which is derived entirely from traditional electrical constants of L, the magnetic field, and C, the electric field, does that still apply to the way light behaves in a glass medium?
Or have physicists had to abandon the square root of L over C model entirely and develop completely new non-traditional physical principles to contend with wave purity, prevent internal reflections, and optimize energy transfer at the speed of light in glass? The fundamental challenge of maximizing power transfer never ends. It just changes mediums.
A deep concept to consider as you think about the future of global communication infrastructure. Thank you for diving deep with us.